Okay, ladies and gentlemen, let's finally proceed to the final section of our workshop. We're going to have 9 talks by Russian researchers. And the first talk is going to be on skill-based conversational agents by Idris, Yusupov, and Yuriy Kuratov.
Hello everyone. First of all, I would like to thank organizers for giving us the opportunity to tell you about our work. The work title is Skill-Based Conversational Agent. My name is Yuriy Kuratov and my colleague is Idris Yusupov. We are PhD students at Moscow Institute of Physics and Technology. Our supervisor is Mikhail Arkhipov. And I think that our work is some kind of outlier of this workshop, but I hope that it still will be interesting for you. Okay, let's start.
Try using arrows.
Yeah. Okay. Let me begin with the plan of my presentation. First of all, I will give a brief introduction into conversational agents, and we will try to define how to differentiate them. Then I will tell you about Conversational Intelligence Challenge at NIPS conference, in which we are participating with our skill-based conversational agent. And the last part of the presentation will cover details of realization of our agent, and Idris will tell you about it. So, what's a conversational agent? In general, conversational agent can be any system that operates with human using voice or text messages. One kind of such conversational agent can be personal assistants like Siri, Cortana, Alexa, or some chatbots in Telegram and Facebook messages. In this talk, dialogue systems, conversational agents, chatbots, dialogue agents, all this terminology means the same, just conversational agent. So, how can we differentiate conversational agents? Two-dimensional plot comes on rescue. There is on horizontal axis we can see the main area of agent, and on vertical axis there is the task that agent should solve. Let's begin with examples. First goes pizza bot. Pizza bot is a bot that will order pizza for you. It asks what kind of pizza do you prefer, where do you live, and so on. It lives in. It has a well-formulated task to order pizza for you and lives in closed pizza's domain defined by pizza's delivery service, for example. So that's why it's a closed domain and strongly task-oriented conversational agent. It's a closed domain because it can book you a plane, for example. And here is artificial intelligence. It can do whatever you want in any domain. It's a far perspective. Is there something between them? Yes. Somewhere between them we can find personal assistants, which I mentioned before. They're not so. They're task-oriented systems, but some of them some of them can just discuss something with users, like chit chat. but also they are not so close domain because they have some number of predefined domains in which they can work, but it's not so close as pixels board. And here is a conversational intelligence challenge boards. And now I will describe this challenge in more details. The main purpose of this challenge is to develop a dialogue agent that can discuss news article or Wikipedia article with a human. All this is happening in Telegram Messenger, and bot and human discuss the paragraph, and or human discuss the paragraph, and at the end of the dialogue, human evaluates overall quality, and also human evaluates every bot's replica. 6 teams. There are 6 teams in this challenge. One team from Russia. It's our with Idris team. There were human evaluation round in July. During this human evaluation round was released a data set of about 2,000 dialects with markup, and it's freely available by this link. And finals of this challenge will be in on NIPS conference. You can follow this link to talk with bots and help organizers and to help participants to collect the data, or you can just search in your Telegram Messenger bot and start chatting with him. And here is the leaderboard of this challenge after human evaluation round. Our team took the 2nd place. It's really close to the 1st place, and 3rd place is too very close to us. But this final score is average overall quality of the dialects that bot finished discussing with humans. All scores are from humans. And the next part will cover details of our bot, and Idris will tell you more about this.
Okay, thanks. First of all, let's again return to conversation about text. How we can define it. So we have the paragraph of text, we have some dialog context, and we have the current articles. All of that data is given to dialog system, and dialog system should return some response, which will be best for the dialog. And the dialog system may, for such case, it may answer something like yes, I'm familiar, or dialog system may ask a question, or it may give some irrelevant response. So it's all about question about skills. What dialog system should be able to do to work good. And what is the skill? Skill is some narrow model. For example, it's question generation. So dialog agent should be able to generate question for the text. For example, some factoid question. It should be able to answer to user question about the text. It should be able to chit-chat about anything. Maybe it will be necessary to have summarization skill, because user can ask about, can you summarize for me this long text into sentences, etc. And we can implement such skills by using, for example, sequence-to-sequence neural networks, by using some retrieval models, writing some rules and templates. So we have a lot of skills that we need to implement. But so now we have another question: how to manage such skills? How to know when we should ask question or summarize? We can do it by modeling conversation with finite state machine. In the slide you can see finite state machine for 3 skills. It's chit-chat, question answering, and question generation. Even for such simple case, they are very hard to maintain finite state machine. And when the skills count will be growing, finite state machine will be harder and harder to maintain. So our approach is about getting rid of finite state machine and focusing on skill implementations. So first of all, we want to get rid of finite state machine. So we need to collect dialog data. We can do it by using, for example, Amazon Mechanical Turk, by writing some simulator. When we have such dialogues, we can build some black box which decides what skill to use for the given dialog. And when we have such black box, when users send message, such black box decide what skill to use and what utterance to generate. We can improve such black box, for example, by using active learning, by using new collected data dialogues with user. We can also we need to support adding new skill to the black box because skills are not fixed. So this is our approach. This is our big picture. It's how we see the conversational agent. So let's go to the part what is done for current moment. We built we built several skills. For example, it's question generation skill, which takes as input text, answer and generate question. We have a chit-chat skill, which trained in Facebook news dataset. As input it took news from Facebook and comments, and as output it predicts next comment. And we have chit-chat and open subtitles. It takes as input subtitles and predict next subtitle. All of that models trained using sequence-to-sequence models on open neural machine translation framework. It's all available in open source. Also, we used question answering skill. We used a BDAF model, which is released by Allen AI Institute. We just write the web server and Dockerize it to use it simpler. As input, it took text and a question, and as output, it returns the answer to the question. Also, we implemented 3 rule-based skills as greeting skill, common question asking skill, and checking user answer correctly skill. So we have that skills in our current dialog agent, but let's see how to manage them. For managing that skills, to know when to use what skill, we built, first of all, we built fast text classifier. As input, it takes a data set of the skill, and as output, it returns a skill which we need to use for the given utterance. For example, if we pass to the fast text classifier open subtitles data set, and we train it to predict the open subtitle chit-chat skill, etc. And for other data sets, it is the same. Also, we have 3 rule-based skills, or rule-based classifier. It's a question asking template. For example, when users utterance starting from ask me a question, it runs the question generation skill. And when generated utterances from our dialog agent is inappropriate, we're using common question asking skill. And when the dialog starting, we use greeting skill. This is our current baseline skill classifier, but of course we would like to improve it for the December. Currently, we baseline done by using non-conversational data. We just use data sets of what skills are trained. But now, after the human evaluation runs in July, we have some conversational data, and we can build a scorer which handles a dialogue context, and it should work better than the current dialog scorer, but the disadvantage of current dataset, because it have all bots dialogues, but we need only ours. So we may need to use mechanical chop to collect more data of our dialogues. And also we build, for improve our classifier, we need to build the dialog evaluation scorer. We built two evaluation scores by, again, Convey human evaluation dataset. First, both of scorers are word-level recurrent neural networks with Yuriy units. And first scorer is scoring the current utterance by handling context and utterance, and returns two labels, poor or good utterance. And the second scorer is overall dialog quality scorer. It returns three labels, poor, natural, and good. It returns score for overall dialog. And when we have such scorers, we can improve our dialog engine more. So there is our future work plans. First of all, we're planning to improve classifier by using current utterance quality scorer. We're planning to collect more data by building setup for human dialog evaluation. We're planning to realize bot with bot conversation using dialog scorer. We're planning to improve the classifier and current utterance dialog scorer by using freezed overall dialog scorer. It is like when AlphaGo bots play with himself. Maybe it will improve the classifier too. Also, of course, we are planning to improve skills and adding new skills, such as summarization and table-based models. And in the end of our presentation, I would like to summarize it. First of all, a conversational agent requires a lot of skills, and we need to know how to manage it. Skill, it is a narrow model. For example, it's question generation model or question answering model. Conversational agent requires management of such skills. We can do it by using finite state machine, but it is very hard to maintain for big count of skills. Our approach helps to get rid of finite state machine and focus on skill implementation. Main idea is to use classifier, which decide what skill to use. And there are a lot of future work until December, and you can talk with our children bot by link, and that's all. Thank you for your attention.
Any questions?
So, what is the human score in those metrics? You showed in the second slide.
What?
Score? You showed a score of 2 and something of your bot.
Scores?
Yeah. What is the score of human to human?
Human to human score.
Yeah. How do people score dialogues with humans?
How people score dialogues with humans.
Like, what is the maximum of this?
Maximum, this is 5. But we don't have data. We don't have numbers. We have data, but we don't calculate data of humans.
Is it possible to find out what the other teams are doing?
What other things to do? I don't know. I think you hear something.
As you know, most of the solutions are closed. They will be open sourced after when competition will over. But I know something about the bot on the third place. I heard a little part of their presentation. They used nearly the same idea to maintain some predefined skills and to learn a policy how to select these skills. What are inside other bots we don't know.
Can you show some examples of
real dialogues with bots?
You can, sorry, no, but you can go by link and try by yourself.
We forgot to include this.
Yeah,
We can try it out later.
You use different models for different skills, yes, and choose between them, or same models.
different models, yes.
Okay.
The weights are not the same. Weights are different.
No, not about weights, but about architecture.
No, for example, for the chit chat, Facebook News and normal subtitles, they are pretty the same, sequence to sequence. And for the question generation too, it's the one model.
Any more questions? Okay, thank you guys. Let's thank the speakers again. Sorry for the delay. Our next speaker, Mikhail Arkhipov, is going to tell us about named entity recognition, specifically in Russian language, specifically using neural networks.
Yeah. Hello, and my name is Mikhail Arkhipov, and I want to present you my summer internship work. It's devoted to application of neural networks to the problem of Russian named entity recognition. A couple of words about the task itself. What are the named entities? We call named entities such things as human names. For example, Jan or Joshua. Organizations like DeepMind. Locations like Red Square or maybe Milky Way, Orion, Spiral Arm, or something like this. Time expressions like 1 billion years ago or 5 o'clock. Quantities like 1,000 spaceships, or monetary values like $20 or something like this. So it's kind of easy to understand what we're trying to find. On this slide you can see an example of a sentence with named entity markup. Each type of named entity highlighted with a specific color. So here you can see 4 types of named entities. It's not a common task, so usually you have to find 1 or 2 type of named entities. So now we're going to talk a little bit about metrics. Named entity corpora usually unbalanced, so there are about 10% of named entities and the rest is untapped. So we need specific metrics like precision, recall, and F measure. These metrics are usually used for evaluation such task as named entity recognition. A couple of words about approaches. There are three main types of approaches existing right now. The first one is rule-based approach, and this approach requires no data. However, it requires some linguistic competence, and it uses extensively such things as dictionaries and regular expressions and handcrafted rules. So if you have a brave linguist and you have no data, it's your option. A little bit more recent alternative is the machine learning approaches. There are two types of models like conditional, like random fields, and support vector machines. These models require a little bit of data with named entity markup, and it uses linguistic features as an input. So you also have to design some linguistic features, for example, whether the word starts with the capital letter or not. It's a simplest case of linguistic feature. It works a little bit better in most of the cases, but we can do even better by applying neural networks. Neural networks is the most recent approach, and this approach is most promising because if you have a lot of data, you can build a simple neural network and don't think about any linguistic features and any language-dependent things. Just train this neural network on large corpus and get nice results. It's a pity, but there is only one work devoted to Russian identity recognition with neural networks, and it uses character-aware digital STM. It's a simple model which tries to predict tag for every character in the sentence. And our work is devoted to extension of this model with something, some models that provide state-of-the-art results on named entity recognition in other languages. We started with a simple model. It's a bidirectional long short-term memory. It takes as input distributed representation of the words and produces probability distribution over the possible tags. So these distributed representation, also known as embeddings, are learnable parameters. Here on the table you can see the results. The first guy applied conditional random fields on linguistic features and got nice results. The second one applied character-aware LSTM, so the results was not so good. And our model provides good recall, but precision and F measure is not as good as it could be. So we can do better. We can extend this model by putting a conditional random field on top of the bidirectional LSTM. Conditional random field is undirected graphical model. There is only approximate inference provided by this model. However, as you can see, there is substantial increase in performance, more than 10 units. So, despite the fact it's not so easy to train, it provides really good results. So, it's a must-have option. But we can do even better than this. We can not learn embeddings, but provide some pre-trained embeddings. Here we replace learnable embeddings with pre-trained embeddings and character-level embeddings. Word embeddings are embeddings provided by fast text algorithm. This is nice algorithm like word2egg, but it provides really good performance, really good word embeddings. And character-level network. It's just a bidirectional LSTM which takes as input a single characters and produces a word representation. It's really useful when you have out of vocabulary word and you have no information about word embeddings. It's just unknown token. So as you can see, you can get extra 2 points of the matrix if you apply good embeddings and enrich it with character level information. We performed a series of tests, series of experiments with different corpora. To the best of our recollection, here you can see all available Russian corpora with named entity markup, except the last one. The last corpus, as you can see, it's enormously big, and there is no markup for this corpus, but we used this one to pre-train our embeddings. On this slide, you can see the results that we get compared to other published results. So, for the most of cases, for first two data sets, we got better performance than other authors. For these corpora, neural networks work better. And the last corpus, you can see that recall is better, but the precision and F measure is not as good as it can be. We actually don't know why neural architecture fails on these type of tasks, but we have some clues about linguistic features that other authors used. For example, Ivanitsky and Bazharova, Ivanitsky and Sisoyev used conditional random fields with really clever linguistic feature design, maybe task specific or maybe specific. They design really good features specifically for this data set. So you can get really nice results with this type of architecture. We also performed a series of tests with open source framework for named entity recognition. It's kind of fresh. It was released, as far as I remember, May this year. And it has similar structure. The architecture kind of the same, but there are some differences in cell structures and initialization strategies. We extended this framework with a number of highway networks. Actually, we were inspired by the character-aware language models that produce really nice results without token embeddings. And these type of networks use dense layer to get deeper representation of the input context, and use a sigmoid gate layer to balance between deeper and more shallow representations. You can see in the formula right here that X is an input, G is a gating function, and H is a dense layer. All of these terms have same dimensionality. So we also try to extend our model with highway networks on top of the word level BayesGroup.ru. These highway networks allow us to balance between raw word representations and representation of context generated by bidirectional LSTM. And here you can see the results. This is the model we discussed first, and this is neural. As you can see, different cell structures and maybe initialization strategies might cause substantial difference. So the first model gives better results. There are a lot of numbers. I will highlight some of them. The first model, not in neural, gives better results. And what about some extensions of the neural model? I want to highlight the character highway network produces better results in most of the cases. So it could be a possible option. You can extend your character network with the highway layer on the top and get some better results. The results for highway network for word level representations is not as good as expected. It's kind of the same, sometimes lower. So it might be better if we stack several layers and provide each layer with highway skip connection. So a single layer with highway extension is not as good as we expected, and surprisingly, combination of these highway extensions produces low results, and I think it's not a good idea to stack some complicated things, and you have to experiment with it to determine which combination works well or not. So the combination of highway character level and highway word level is not as good as it could be. So in conclusion, I want to just to say that we have performed a number of tests on all available Russian data corpora with maintaining markup. For some corpora, results exceeds current state of the art, which is good. But for some, for one corpus, we get appropriate result, but not the best one. And I think that the bidirectional STM and CRF is a suitable model for Russian mirror task. And I think some extension of this network could provide even better results. I want to thank my sponsors. It's an agency of strategic initiatives and Sberbank. Actually, they support our project. It's an iPower project, and that's all. That's all.
Any questions?
Yeah, so first a comment. I mean, it looks like there's a lot of programming work in this.
Yeah.
It looks like it's a huge effort.
Actually, we have extensively used some open source solutions. So modification of networks, it's not some difficult thing to do because you spend a lot of time to prepare your data, to feed your data in correct way. So actually, there is not as much programming work as can be seen.
Right. So the other thing is you've got the CRF on top.
Yeah.
I have no concept of what you're doing there. Can you give us some intuition? And secondly, have you actually explored any other languages?
This model has been implemented in many different languages except Russian.
Oh, the CRF on top.
Yes, actually the inputs to the CRF are context representations generated by the bidirectional STM.
So they're effectively features for the CRF to use?
Yes, exactly.
Oh, wow.
Yeah. It works like this. So in machine learning case, there are linguistic features. Linguistic features are used as an input to CRF, and in our case, representations generated by LSTM used as an input to
But how does the neural net get the training signal?
Sorry?
Well, how does it get a training signal? I mean, it's got to be...
The training, it's regular maximum likelihood training.
through the CRF and down through the...
Actually, you're asking about how the gradients propagate through the,
Yes.
through the CRF. So, like in it propagates like in restricted Boston machines or other undirected graphical models. So it's a stage sorry, I'm struggling. I'm struggling to
That's
explain
right,
it
you've answered the question.
in English.
Good. Thank you.
So you're saying that those models with serifs on top, they have been tried out in different languages?
Yeah, yeah.
In case when you don't use any specific linguistic features, does the performance differ significantly?
Actually, we can look at for example, this type of model gallery uses linguistic features and the and CRF, and this type of model use LSTM and
Okay.
CRF.
And what happens when you change the language but use the same model? Does the performance change significantly?
It heavily depends on the language.
Okay.
So I think there is no clear answer to this question because it's language dependent. I think similar languages should have similar performance on this task.
Do they?
As far as I remember, the results of these architectures for some European languages are quite the same. And it is also data dependent, so it depends on what kind of corpus do you have, and so the quality of the data might differ. So it's not so easy to answer.
Now I'm happy to invite our next speaker, Konstantin, has agreed to participate in our workshop and give a talk on additive regularization for topic modeling.
Здесь ничего не видно. Dear colleagues, my talk about topic models. I'm Konstantin Vorontsov from Moscow Institute of Physics and Technology. I give lectures on machine learning also in Moscow State University and in Yandex School of Data Analysis. Here, two companies. Forexis is a 16-year-old company in Russian market of business intelligence and data analytics, and ITER is our very young and very small company, 1 year old. My plan will be straightforward, so theory, implementation and applications. Topic modeling is widely used for exploratory research in digital libraries, for social media analysis, for information retrieval of texts by images and images by text, for topic detection and tracking in news flows, for navigation in big text collections, and also for conversational intelligence, dialog managers, etc. So there are many applications of topic models. What is a topic in a text collection? Intuitively, topic is a specific terminology of a particular domain area, or it is a set of terms or words that often co-occur in documents. But more formally, in statistical language modeling, we can say that topic is a probability distribution over words of terms, and each document can be represented by a distribution, or probability distribution over topics. And here is our hypothesis that when writing term W in document D, author's thought of topic T, but the author's thoughts are hidden, latent for us, so topic model uncovers the set of topics and uncovers the thoughts of authors of documents. Our formal problem statement is follows. We have a document collection, D, and we know how many times each term appears in each document. And we want to find parameters of the model, word distribution in topics, and topic distribution in documents. And this model that explains the word occurrence in documents by topics, this model can be represented as non-negative matrix factorization. So we have our initial data words in documents, and we want to know words in topics and topics in documents. One standard way to solve this problem is log likelihood maximization in probabilistic latent semantic analysis from Thomas Hoffman. And well-known Karush-Kuhn-Tucker conditions can be used to solve this problem and to reduce this problem to the nonlinear system, to the system of nonlinear equations. We can solve this system by sample iteration methods. And it is interesting that this method is strictly the same as the EM algorithm. So at E step, we estimate the topic distribution for each word in each document. And this is no more than Bayes' rule. And the second M step is frequency estimation of conditional probabilities of word and topics, and of topics in documents. So this is a very intuitive system that can be solved by EM algorithm. Here also I introduced a very convenient notation. Norm x t is a vector operation that takes the vector x and gives the normalized vector of the same dimension. We have the bad news that this problem is imposed. It may have infinitely many solutions. So there are here linear non-uniqueness of the solution, and also the non-linear non-uniqueness. And the classical way to solve imposed problems is regularization. So we can add some regularization criteria. And the good news is that in applications there are many reasons for introducing additional criteria for make the set of solutions narrow. So this is the scheme of topic modeling. We have observable data, and we have a hidden space, the space of model parameters. Generative process generates the text collection from parameters, but we solve the inverse problem, how to identify the parameters given the collection. in the observable data. But in practice, there are many additional data in applications, for example, meta information about documents, linked data, transaction data, the data about users, some linguistics, the linguistic data, and so on. And also parameters can be much more complex than phi and theta matrices. We also can identify the parameters of temporal dependencies, of hierarchical structure of topics, some relations, correlations, we can solve the supervised learning task and so on. And also there are many requirements for the topics, which must be interpretable, sparse, different, and so on. The most popular approach to topic modeling is Bison Approach. In Bison Approach, we model the generative process which encapsulates all our knowledge about the hidden space structure, the prior distributions, and all our assumptions and requirements. And Bison inference is the universal way to make the inference of such a model. But this approach has limitations. The artificial complication of the task is that our generative process encapsulates all we know about the problem, and because this estimation of posteriors is a difficult task. Nevertheless, posteriors are used only for point estimation, only for estimate the expected values of model parameters in topic modeling. In that point, I make the message that maybe Bisons solve a more difficult task than it is necessary for probabilistic topic modeling. And from this, many limitations stem. First, the solution requires a lot of mathematics and coding unique for each model. Second, there is no way to unify models in a Lego-style modular technology. There is no easy way to combine models. No way to impose non-probabilistic constraints and to specify optimization criteria, additional optimization criteria for the model. So our approach is to come back to the classical non-Bayesian regularization. We use only very simple generation of processes to describe our hidden space, the structure of our hidden space. And we try to describe most of our requirements and assumptions by means of regularizers. And second, we propose to use additive regularization. So many regularizers can be mixed and interchanged. How to do this? This is a classical model, latent directly allocation. The first Bison model in topic modeling. With this model, we can do the non-classical reinterpretation, and the logarithm of directly prior is the same as cross-entropy regularization. And our EM algorithm from probabilistic latent semantic analysis can be easily generalized for this case. The generalization is to add the smoothing parameters in the frequency estimates of conditional probabilities. The next step of the generalization is to use an arbitrary regularization criteria, and it is very easy to pass this arbitrary function to the final system of equation. And so we can substitute here R and solve this system for any R. The next step of the generalization, we can use the combination of regularizers. So we can interpret any Bayesian probabilistic topic model with any prior as log likelihood maximization with regularization. And after this, we can combine many topic models if we split the topic model to the space structure and regularizes. So we can use the same space structure and regularizers taken from many probabilistic models. The next step of generalization. There are many applications in which not only words are in documents, but documents are universal containers that contains words and other modalities such as authors, timestamps, categories, tags, links, and so on. The generalization is very simple. We can use a log likelihood for any modality as an additional regularizer. And our system of equation have a little modification, so all technology can be, technology of solving, of numerically solving this equation can be reproduced for this type of generalization. Thus, we can solve practical tasks of topic modeling by combining building blocks. What are our building blocks? Here is a series of some slides where I show that many traditional models, in topic models, that traditionally was introduced in Bayesian terms can be easily rewritten and restated in our framework. For example, if you want to have background topics to describe the general lexis words, we use the smoothing regularization for these topics. If you want to make our topics very sparse, we also can use a regularizer, but this regularizer cannot be expressed in Bayesian terms because in Dirichlet prior we cannot use negative coefficients, but if we interpret this criteria in non-Bayesian terms, this is possible. Next, we have a very simple regularization for make topics as different as possible. And if we combine all three regularizers, we can make topics more interpretable. The next series is also topic models that first were introduced in Bayesian frameworks. We can use hierarchical topic models. We can build them level by level, and we can use for this the regularizers that links between parent topics T and their subtopics S. We can also build temporal or dynamic topic models with the restriction that the dynamics of topics cannot be too noisy. The next, we can use a special regularizer to solve the regression problems where we predict some numerical output for text documents. This case is very interesting because it answers the question how many topics we need. In Bison approach, here complicated non-parametric Bayesian methods are used as Chinese restaurant model or hierarchical Dirichlet processes. But in our framework, this problem becomes very simple because we use a regularizer that makes topic selection. It selects only topics that are needed for the model. There are many cases for multimodal topic modeling. So modalities can be classes or categories for text classification and categorization. Modalities can be languages in many multilingual applications of topic models. Modalities can be, for example, graph vertices if we want to use additional information about some links between documents. So each vertex has its own set of documents, and we describe the links between documents. And the particular case of this regularizer is geospatial models, which takes into account geolocations of documents, for example, in social networks. The next is the possibility to go beyond the bag of words hypothesis, which is too restrictive in natural language application. So we may use n-grams of collocations as modalities. We can use SyntaxNet, for example, as a pre-processing tool for build a multimodal model with n-grams as modalities. We can use the information about co-occurrence data, and for example, in order to build topical word embeddings, and this will the topic of the next talk of Potapenko. And finally, we just know that how to build regularized topic models that make segmentation of texts. This is also beyond the bag of words hypothesis. How to do this? To do this, we use a regularizer that is a function of hidden probabilities of topics for each word in each document. This is a three-dimensional matrix. And if we define the regularization criteria on the parameters of this matrix, thus we must modify our system of equation such a way. This is not a very complicated modification, because the only thing we must do is to differentiate our function r by parameter speed. So not more complicated than in gradient descent methods, for example. There is no complicated inference in our approach. The next step is to propose the implementation of our approach. We implemented it in open source project Big RTM. This model is parallel, online, multimodal, and it is free available at very permissive license. So for both academic and commercial use. Here's the main engineering idea of this project. The main idea that if compared with Bison Approach, we can unify many stages of applying topic modeling in real-life applications. So if we design a Bison model, we need to do mathematics and coding in each stage of your research and development. But in our framework, we may unify many stages, like here, and occupied by designing only your own criteria and your own measure of quality for topic models. Benchmarks show that we are faster than our concurrent in a data set of 3 billion of articles from Wikipedia. And finally, in my talk, I briefly show how to solve applied problems using our framework. The project of mining ethnical discourse on social media, the goal is to find all ethnical topics for monitoring inter-ethnic relations in social media. So we have about 300 ethnonyms as seed words, and we use the combination of regularizers that make our model interpretable. Multimodal because ethnonyms is a modality. Temporal because we want to monitor the changes in our ethnically related topics. And geospatial because we want to know in what regions people discuss our ethnically related topics. The next example is exploratory research by long text queries in technical news. Here we use also the combination of regularizers for interpretability for multiple modalities such as text, categories, authors, and n-grams. We show that precision and recall is very high, and that our exploratory research topic-based system instantly performs the work that people typically complete in about a half of an hour. One more application is topic detection and tracking in use for media planning. This is an ongoing project, and here we use also interpretability, hierarchical structure, temporal, multimodal and gram, multi-language, and so on. The combination of regularizers that help us to solve this very difficult problem. And finally, one application is scenario analysis of call center records. Here our goal is to determine typical scenarios of call center dialogues between operators and customers. We use the regularizers again for make topics interpretable, for make segmentation. We use n-grams, we use syntax, and we use special regularizers that take into account the sentence structure of texts. Summary. Additional regularization of topic models is a new non-Bison regularization frameworks for probabilistic topic modeling, which gives the easy way to formalize and combine topic models. And also it makes it easier to understand and explain the topic models. It originates the topic modeling technology in modular Lego style, so we can solve practical applications, but by combining the building blocks for our separate topic models, separate regularizers. The BayesGroup.ru project is open source project, a 4-year-old project at GitHub, and so we are using RTM for mining. Now we try to using RTM for mining transaction data of any nature, for example in banking. Finally, welcome to use and make contributions in BayesGroup.ru. Here is our publications. Thank you. Questions?
Yeah, obviously we should have a longer discussion afterwards on the. But I know I said in my talk on Monday, I think, about the role of regularization, which I see as a way of relaxing you from the constraints of Bayesian reasoning, which require normalization and various other things. And so, for instance, allow this modularity and Lego activity you're talking about, but the difference usually is in the regularization works for different, well, sometimes in the smaller data sets, the Bayesian methods are or expected to work better. And that's the main difference, I understand it. But anyway, that's a comment just on the general talk. But the other thing is, you've got all of these constraints you put on. Usually when we do those constraints, we put on trade-off parameters, right? Because we do a lot of this as well in other work. So you've got a general optimizer, and then you've got a bunch of constraints. And each of them you add a lambda, and then usually like we use cross-validation or something to fit them. Are you doing that in this, or? Am I reaching? You know, so you've got your main fit, but then you've got all of the extra constraints, which are like you want sparsity, you want something else. But each of them you usually put on a trade-off parameter.
Yeah, you mean, may interrupt you?
Yes, I improve some difficulties with English. Your question is very interesting, but I didn't understand it.
Oh.
So, do you mean hyperparameter regularizers? Hyperparameters like coefficients of our regularizers?
Yes, so whenever we do, because we do a lot of regularization, so when we do it, we add a hyperparameter on each of the constraints,
yes.
And then we have to do an extra step of cross-validation.
Yes, so it's definitely like a big question for us, and still kind of an open problem. How do we tune those hyperparameters?
Yeah. Well,
So usually
there's no magic solution.
Yeah, no magic solution. So we usually just use some training data or some development validation data to tune this. We look into multiple criteria, like perplexity, coherence, sparsity, and all the other kind of measures that we want to look into, and we see how they change in iterations, and this way validate and tune our hyperparameters to find this right balance. Yeah, but that's a good question.
We have several techniques. For example, we use coordinate-based optimization of hyperparameters.
Okay.
One by one.
Yeah.
Any more questions? Okay, let's thank the speaker again. Our previous talks were concentrated mainly on language applications, and Anna's talk is not going to be an exception.
That's true.
This is the final talk in our NLP block. After this talk, we'll have a 15 minutes break, and Anna is going to present work on Interpretable Probabilistic Embeddings.
Yes, right, but I have no idea where is my presentation, so if you...
I thought you find it. Here.
Yes.
Sorry.
Okay, hi everyone, and I'm glad to see you. I mean, I'm really glad to see you, because now I'm making videos for Coursera NLP course, and you know, it's kind of creepy to make a lecture in an empty room with a camera, so it's much better like that, and please feel free to interrupt with any questions, it's totally fine. So, interpretable probabilistic embeddings. Something in between two worlds, topic models and word embeddings. Sometimes people ask me what I'm working on, and I say, well, I'm working on topic models. And people say, oh, this is LDA model with those Dirichlet priors. And it seems like this picture of a generative process arises in their minds. Sometimes I say that I'm working on word embeddings, and people would say, okay, this is king minus man plus woman equal to queen. Sure, this thing. So the goal of my talk today is to kind of show what are other models around these two, and to show that actually these two models are not just two irrelevant models in machine learning world, but they really deal with a very similar task. So to do this, I want to have a step back first and give you some 2 slides introduction on distributional semantics. So it is semantics, it means it's about meaning of words, and it is distributional, which means it defines the meaning of the word as a distribution over other words. So we can calculate how many times the word be occurs with other words. By co-occurrence, I mean that they occur in a window of a fixed size in our text. Okay, we can see that bee and honey occur really a lot, so these two words are kind of related. But usually this is not that relatedness that we need in our applications. So usually we want to find words that are kind of examples of the same category or some synonyms, and that's where we need a second step. So first we need to compute those concurrence vectors, and then we need to find some similarity between these two vectors. This will give us a digit that will be a good similarity measure for bee and bumblebee, let's say. Now, one drawback with this approach is that you deal with long vectors, as long as the size of your vocabulary. So an obvious next step would be to build a matrix with these rows and perform some dimensionality reduction. Okay, and this is what people have been doing for years, or let's say for decades of years. There is a nice zoom of these models with different types of concurrences in the first matrix and with different types of dimensionality reduction technique. And you can find this in this survey. But what's important for us now is that the outcome of these models is 2 matrices, phi matrix and theta matrix. T is the size of our hidden low-dimensional space. So the rows of phi matrix are the word embeddings, some vector representations of words that we are going to use instead of long rows of our original matrix. What about theta matrix? Well, theta matrix is not so lucky, and usually it is just thrown away in the models, or at least sometimes. I'm not so cruel, and I feel a little bit sorry for this pure theta matrix. So I'm trying to tie the parameters and to say that somehow phi and theta are related, and then we can build models with the same accuracy but with twice less parameters. But this is a little bit other direction. So for now, I want you just to remember that we have phi matrix and theta matrix with our low-dimensional representations. So far, so good? Okay, so now we are good to come back to our comparison. This is probabilistic latent semantic analysis model. What it does, it says, let us model probabilities of words in documents. Let us do this by a mixture of topics. We will have 2 matrices of parameters, phi and theta, and they will be filled with probabilities. Probabilities of words and documents, probabilities of words and topics, and probabilities of topics in documents. Okay? So we will build our model, we will use EM algorithm to build this, and we will just have a mixture model, because we have already normalized probabilities, which means we can just mixture them and have our target probability. Now, what's happening with Skibra model, which is a well-known architecture of word-to-vec? Here, we also have 2 matrices of parameters, phi and theta, but they are real-valued. So we need extra step, we need softmax to get normalized probabilities. The second important difference is that for skip-gram model, we model probabilities of words given other words. So by U and V, I denote just two words that occur in a sliding window again. Let's say a window of size 6 or a window of size 10. So two differences, otherwise completely similar framework and similar task that we deal with. Now, this model is good with interpretability. We get some topics that are interpretable. This one is good with word similarity. We get some vectors that represent similar words in similar places of our space. Can we combine that somehow? We can try. So we can say, let us predict word-to-word co-occurrences, let us predict probabilities of U given V by a mixture of topics. And let us write down our likelihood, as we can do, and let us also have constraints, because we are going to have probability distributions here and probability distributions there. A similar model was proposed in Word Network topic model paper, and they said we want to deal with short texts. Short texts usually provide very sparse Word document matrices, so they wanted to use some word-to-word data. But they never studied this in regard of word embeddings. So now we propose to use this approach for word embeddings. We can have the next step, and we had a great talk by Konstantin Vorontsov about additive regularization of topic models. So we can just add this approach on top of our probabilistic word embeddings. We can have additional requirements for our embeddings. We can plug them here, and for example, we can have sparse or diverse embeddings. We will come back to that. Now, just a sketch of the algorithm, because I guess I have no time to explain it in details. I guess many of you are quite familiar with EM algorithm. What it does, it says for the E step, we evaluate posterior probabilities for topics in our corpora, and for M step, we update our perimeters. So one trick here is that probably our word-to-word occurrence matrix is huge. Probably we can compute this, though it's already not so easy, believe me. But probably we don't want to store it in memory as a whole. Also, we do not want to update our phi once all the data is passed through. So what can we do here? Well, we can split it. We can split it into blocks, and we can notice that theta updates are independent by columns. So I can use the first block, and I can iterate on this with updates for posterior probabilities and for theta here. Then I can forget about theta and use my posterior probabilities to do some incremental updates for phi metrics. So phi metrics will be incrementally updated between these blocks using posterior probabilities that have converged here. Okay? So this is just a sketch of the algorithm, and you can find more details in the paper or in bigger TM implementation. So one last thing to mention here in this part of talk. You can definitely see that topic models provide some matrix factorization, right? This is stochastic matrix factorization, which means we have additional constraints for parameters. What about other methods? It is well known that skip-gram negative sampling is also implicit matrix factorization. So this is kind of an ugly table that I don't want you to read now in details. All I want to say here is that different techniques like global vectors, non-negative sparse embeddings, and other embeddings all can be summarized in 4 steps. We define what is the type of the matrix here on the left. We define what is our objectives and constraints, and we decide whether we build this model with stochastic gradient descent or EM algorithm or any other optimization algorithm that we like, right? So, take away from this part. For now, we have discussed that topic models and word embeddings are rather similar things, and we can try to build some hybrid models, and we could understand it from theoretical side. Now, is it useful? So, is it really performs okay in practice? Let's see and let's test that. So, how we can test that? There are a lot of questions on how it would be good to do evaluation properly, but and linguists can know a lot about similar words and different types of similarities, and also it's better not to look into similar words, but just to use our downstream tasks, our final applications, because something can change. But nevertheless, all these papers in this flow of research fall into these evaluation techniques. We have some human judgments, some well-known data sets, some benchmarks that look like that. So we have word pairs that say, well, tiger and cat are kind of similar, tiger and tiger are even more similar, and so on. So we have some human ratings, right? Now we can make our model to predict similarities by the model. Remember those cosine similarities between some vectors, right? And we can now compare these rankings. For example, we can compute Spearman correlation and say whether our model can predict this ranking. Let's do this. Don't be afraid, I'm going to walk you through line by line through this table. So the first line is skip-gram negative sampling, which is a well-known kind of state-of-the-art word embedding technique. What it does, it uses shifted PMI information as the original data. It implements stochastic gradient descent, and then when it builds the embeddings, it uses cosine similarity between them to provide those similarity rankings. Now, the next line is LDA, and you can see that it performs really poorly. So this is where usually the research stops in the papers and people say like, okay, topic models are not a tool to provide word embeddings. But let's look closer. So LDA uses word document statistics, and it uses Hellinger distance between our topical probabilistic embeddings to compute similarities, which actually sounds quite reasonable. So if your embedding is probability of topics for the word, you would better use Hellinger distance to compute similarity between those probability distributions, right? But in our research, we find out that just dot product performs much better than Hellinger distance or any other nice distance. Also, it is, as I have already mentioned, it is crucial to use word concurrence statistics instead of word document statistics. Now, what else? We have tried a lot of different options of data in our original metrics. For example, pointwise mutual information, positive pointwise mutual informations performs well for some data sets, but otherwise it was mostly negative experiments. Now, it was very important to learn algorithms with online EM, and there were a lot of small tricks there that you can find in the paper. So finally we could make our model perform kind of comparable. I'm not saying this is new state of the art or these digits are fancy. No, I'm just saying they are okay. So the test is passed, and we can look what other benefits our model provides. So the first benefit is right here. This is sparse probabilistic word embeddings that has 93% of zeros in our small embeddings. So the embeddings are just 300 dimension, and they have 93% of zeros. The similarity measures are kind of the same for all the data sets, right? So this is first. Next, what other benefits we can have here? We can have 3 benefits, and I will cover these 3 benefits until the end of the talk. So we will have interpretability, document embeddings, and embeddings for additional modalities. Let's start with interpretability. It's really appealing to have something like that. So to say that there are some components that have some meaning. Like there is a component about royalty, and king and queen and princess have a high magnitude there. And there is a component about age, and so on. Well, that's how we would like to imagine and to dream, but this is definitely not as happening with word-to-vec in practice. So if you look into the components exactly into the top words, into the words with the highest magnitude of the components, we will get something like this. So, me personally, I can't interpret this. This is kind of rubbish words. If you go for probabilistic word embeddings, they are still not super fine-grained, but at least they have some meaning. So, this is about Scotland, England, and kingdom and royalty. This thing is about games. This thing is about politics, right? So, it's kind of interpretable topics. Now, how can we evaluate this? Because it's definitely not nice to compare just lots of words, right? People did a lot of work on this as well. So if you have some experts, or if at least you have some money, you can do word intrusion task, which means you get your top words of your components and you intrude one random word there. And you ask your reviewers to find this random word. So they assume that if the reviewers find it easily, then the topic was good, it was coherent. If you do not have experts, no worries. People also developed other ways to evaluate interpretability. So coherence is very well studied in topic modeling literature. It has lots of variants, for example, nicely surveyed here. And it is shown that it correlates with human judgments. So what it does, it says, let's look into pairs of words in our top list. And let's compute point-wise mutual information, which says, isn't the fact that these two words occur together much more frequent than they would if they were independent, right? So in the nominator you have joint probability, and in the denominator you have kind of independent case. So you compute point-wise mutual information and average across all the pairs in this list. And this is how people can evaluate interpretability. So, congratulations, here we have better interpretability than LDA or skip gram negative sampling, and we had several options how to compute this for skip gram negative sampling, because there you have unnormalized matrices, and you can either just take it as is or use Bayes rule to reorder and to say that it will be normalized in the other direction. So anyways, it doesn't help this model. Okay, number second, document embeddings. So people have a task to compute similarity between documents, not only between words. And actually it's not so easy to evaluate these models. However, there is a data set by Walkley and authors that has some triplets of archive papers. It says that we have some archive paper, and we have some similar archive paper, which is also on mathematics, and we have some dissimilar archive paper, which is about some physics here. So let us try our model to understand that this document is more further away than these two. And let us compute accuracy for all those triplets, right? This is what we get here. So this model was trained on archive papers, on plain texts, and tested on those triplets released by those authors. And DIBO is their architecture of paragraph to VEC model, and we could see that here we outperformed it for all the dimensions that we tried. So it's kind of always tricky to reproduce any experiments, so I did my best to reproduce DIBO as they suggested in the paper, though not all the hyperparameters were there, so I did my best. Now, the last part is about embeddings for multiple modalities. So once we have our topic modeling framework, we can imagine that we have some data that has not only text, but it has title, it has timestamp, it has category, it has subcategory, and all other kinds of entities, if you want, that you also want to embed to your space. Additive regularization of topic models is here to help. So we can have our log likelihood for several modalities. We can sum them with some modality weights, and we can optimize this all together as a soup of losses, as was said today or yesterday. So these parameters are our new phi matrix. It is bigger, so it has probabilities of words and topics, and probabilities of authors in topics, and probabilities of timestamp in topics, and so on. Again, no details, just results. So this is evaluation for Russian corpora, Latent rule, which means we used Russian translations of word similarity benchmarks. And here, what's interesting here is that multiple modalities help even for word similarities. So when we use timestamps, suddenly similarities between just two words get to be better. So this last line here is the best for most of test sets. And finally, we can look into intermodality similarities. So once we could embed our timestamps and our words into the same space, we can look into what are the closest words to the Oscars date. And we can see that this is Oscar, Birdman, nomination, and some other relevant stuff. So this thing looks really promising, though it's not quite clear how to evaluate it, not just by looking into it. Okay, that's all. So we have covered 3 experiments right now, and all in all, we have proposed the model that builds probabilistic word embeddings, and we have shown that we can consider these tasks as one task in topic modeling framework and use some benefits like easy extensions that are already known in Bayesian or non-Bayesian topic modeling work, and some interpretability of the components, and something else that we will hopefully do in the future. So thank you.
Sorry, am I right that there is no mathematical evaluation of the results, so that it is more like decided by the testers, by the...
Not really. Well, it depends on what you mean by numeric evaluation, right? So when I show you this thing, this is definitely not quantitative approach, right? It's just decided by people. But when I show you these things, these are kind of very well-known benchmarks in this sphere. So all new word embedding techniques that are proposed are tested on these benchmarks prepared by some linguists that care to have some very balanced similarity types inside and so on. So this is kind of okay. I think it's like a good approach. And the same for coherence as well. It's not just something that you look with your eyes. It's just some numbers that you get out of the model.
Have you tried this? Are there any approaches to make out of this generator that will make text on a specific topic that, for example, your recognizer wouldn't see any difference between it and the human writing? I mean, like in the GANs where...
You mean, well, are you speaking about text generation? Or
yes.
Did I got it correctly? So actually, like topic modeling and as well as word embeddings are not really about text generation, right? So like even though in both tasks we learn by language modeling task, we do not usually use this as a tool to generate language, right?
Yes,
so
I know, but there are some,
some,
as far as I understand, there are some moves towards text generation. And have you tried to use your model to see how it differs from the natural?
Yeah, good question. So indeed there are a lot of work in somehow hybrids between neural networks and topic models that say that let us generate text and let our LSTM model to generate words, but let us topic model provide some topics, right? So yeah, this is something that I would want to look into, but I didn't have time and didn't have this focus yet.
Okay. And can you show, please, again the idea of the online EM algorithm? Maybe there is some article.
Yeah, there definitely is.
So it isn't your idea.
Well, how to say? So there is online LTE.
I mean, it's well. I'm not going.
Yeah, let me briefly
sorry.
say. So there is online LTE proposed by Hoffman in 2011, I guess, 2010. They do this approach for learning LTE on documents. So, and they do this, I guess, with variational Bayes inference. So we use this idea about building about Bayesian, right? But it's a good idea. And we use it for non-Bayesian inference, and we use it for word-to-word concurrent statistics. So here, this is not documents, right? So we have some pseudo documents that you collect by concatenating local context of your words, and this is very key thing there. So this is kind of hybrid between something known by online LTE approach and further work.
So now we have, we're going to have 15 minutes break. Or we don't.
No, we have, I think, like 10 minutes because
Yeah.
we are out of time now.
Let's shorten the break because we're ready.
Please have snacks and drinks there for